Greetings and salutations, magical chemists. In this video, we're going to learn about quantitative electrolysis calculations, or why dimensional analysis really is your very best friend. As you know, in an electrolytic cell, you're often plating out a particular solid product on your cathode. Well, mathematically, you want to be able to determine how much of that product can be made. Well, this is the process to do so. So first we're going to talk through the step-by-step of what the calculation will look like, and then we'll try one. It will be ever so much fun. Before you start any other math, the first thing you want to do is make sure you know the amount of time in seconds that this process is happening. You're going to multiply that time in seconds times the current that is flowing through your electrolytic cell. The current is measured in amps. Now an amp, or ampere, is defined to be a coulomb per second. This unit conversion is not provided to you on your formula chart, but you kind of need to know it anyway. It'll really make this whole process easier, so you might want to make a note that you need to know that. So all you're doing in the second step is you're literally taking the seconds from the first step and multiplying it times the amps. So you'll notice, just looking at the units, right, you multiply seconds times coulombs per second, seconds cancel. So you're solving for the charge in coulombs in the current of your electrolytic cell. Okay, now you got that. Now Faraday's constant comes in handy. We've already worked with Faraday's constant. We know, and it's given to us on the formula chart, that it is 96,485 coulombs per mole of electrons. So this allows us to convert from coulombs, which is our charge, into moles of electrons being transferred. Now, if there's a multiple choice problem, and there will be multiple choice problems, remember, we're just going to round Faraday's to 100 grand. Sorry, that would be money, 100,000. So for this step, you're basically just dividing by Faraday's constant, which means since Faraday's constant is coulombs per mole of electrons, your units are moles of electrons over coulombs. There's an important terminology thing to note. People actually will talk about a Faraday, and that'll be referring to the number of moles of electrons being transferred. It's basically just another chemistry shortcut. So if someone talks about, oh, there were 3 Faradays, that means 3 moles of electrons were transferred. Well, if you had 0.25 Faradays, it was 0.25 moles of electrons transferred. So be familiar with that terminology. So now we know the number of moles of electrons being transferred. But usually, we want to actually find out how much of the metal specifically we're looking at is being formed. So we have to convert from moles of our metal, moles of electrons to moles of our metal. So you have to look at the change in oxidation state of the particular metal that you're concerned with. For example, if we were looking at gold 3+, and we were going to go ahead and reduce that into solid gold, notice 3 moles of electrons were being transferred for every 1 mole of gold formed. So for this step, you're multiplying by conversion fraction, where you have 1 mole of the metal. It's always 1 mole of the metal on top, and then the number of moles of electrons being transferred relative to that metal on the bottom. And then now you're in moles of metal. So easy peasy, go to grams, use molar mass. So you're literally just multiplying times grams per mole. Okay. Let's go ahead and see what a problem of this type might look like when you're solving it. Okay, in this example problem, we are looking at gold, shiny gold. So once again, we're looking at that gold 3+ being reduced down to solid gold. And we want to know, okay, that's great. What is the mass of gold in grams that will be plated out if we have an electrolytic cell with a flow of electrons running for 25 minutes at 5.5 amps of current. So this is where we get to set up the most beautiful set of dimensional analysis fractions ever. Remember our first step, we need to convert our minutes into seconds. And once we have our time in seconds, you go ahead and multiply that times the current in amps. Once we've then converted into coulombs of charge, we use Faraday's constant. So we're dividing by Faraday's constant, and that'll convert from coulombs to moles of electrons. Once you divide by Faraday's constant to convert to moles of electrons, now it actually gets specific for the metal. In this case, remember they even gave us the half reaction. For every 1 mole of gold, 3 moles of electrons were being transferred. And last but not least, we multiply by the molar mass of gold to convert to grams. As far as sig figs are concerned, there are only 2 numbers that we have to worry about for sig figs. there is the charge, our amps, 5.5, and our time, 25 minutes. Since they both had 2 sig figs, our final answer ends up with 2 sig figs. And so that's what a problem like that looks like. It's not exactly short, but it is very systematic. So let's talk about the types of problems you might be asked for doing your calculations for electrolysis. The first type is the one we just looked at, where they gave you the time and your current, and they ask you to find the mass. But these questions can also go backwards. If they gave you the mass that's plated and the current, they can also ask you to calculate how much time it would take. Of course, there are endless variations on these, but these are the 2 basic calculation types. And notice for both of them, we have to tell you what the current is. Now you might be thinking, how in the world am I ever supposed to remember the order of all these steps I'm supposed to do? Well, luckily, I've got a quick trick for you to remember. It's kind of terrible, but it works, so we're going to go with it. And what you're going to remember is to think, are you safe? Here's how that will help. Well, the S in safe stands for seconds, the A for amps, the F for Faraday, you just have to remember to divide by Faraday, and the E can help remind you that that got you all the way to moles of electrons. And then you've got the Well, the first M is for mole, because this is where you're converting from the moles of electrons to the moles of the metal, and then the last of your is for molar mass. And if you're going backwards, this even reverses. Then you get face. So there you have it. Delicious dimensional analysis and a trick to remember it. So let's try some practice problems. Okay, in our first example problem, they say you've got 3.30 Faradays of charge, and that's passed through a solution of Al2SO4 and we want to know the mass of aluminum deposited. You might be thinking, but wait, I only have one number. They didn't give me the current. You said they'd always give me the current. Well, this is one of those weird problems. Remember how 3.30 Faradays is like a shortcut for saying 3.30 moles of electrons have been transferred? We've basically skipped the first 2 steps. They didn't give us time, they didn't give us our current, because they just gave us Faradays. Since we're already at moles of electrons, our next step, actually our first conversion fraction, is just to convert from moles of electrons to moles of the metal we're trying to make, in this case aluminum. Whenever you're converting between a part and a whole, right, we have the whole aluminum atom, that one gets the number 1 in our conversion fraction. And then we do have to figure out, okay, well, how many electrons get transferred for every aluminum atom? Well, now for aluminum, you don't actually need to look at the compound they gave you because aluminum doesn't have a variable charge, but it's always safest to look back to the compound you're starting with, because notice, Al2SO4 has an aluminum cation, and that aluminum cation has a 3+ charge. Of course it does, it's aluminum. Well, if you've got aluminum 3+, and you want it to get to solid aluminum, well, you sure as heck better add 3 electrons, right? Because 3+ to neutral, that's a gain of 3 electrons. So that's why our conversion factor here says that there are 3 moles of electrons being transferred for every 1 mole of aluminum. Once we have that, we've got moles of aluminum, so we just multiply by the molar mass of aluminum. In this case, we get to keep 3 sig figs from our 3.30 Faraday. So we get 29.7 grams of aluminum was deposited on the cathode. Okay, let's try another one. In this problem, it says, well, how long, aka how much time would it take, for a current of 5 amps being applied to a solution of AgCN to produce 10.5 grams of silver metal? So in this problem, they gave you the current and they gave you the grams, so we're going backwards. Since we're going backwards, our mnemonic is face. So the beginning of our is molar mass. So I'm first just going to take my 10.5 grams of silver and use the molar mass of silver to convert that into moles of silver. And then after molar mass, we need to convert from the moles of our silver into moles of electrons. So we need that conversion factor. This time, because we're going backwards, moles of silver are on the bottom, moles of electrons are on the top. Remember, the atom, the whole thing itself, gets the 1. So for every 1 mole of silver, well, we have to look at what silver ion we have to see how many electrons are being transferred. Well, you might just remember, silver, of course, it's a transition metal, but it doesn't have a variable charge. It always has the same charge. But if you weren't sure, you might remember the charge on cyanide. The cyanide polyatomic has a charge of -1, so silver here indeed has a charge of +1. And since silver only has a +1 charge, it only needs 1 electron to be reduced to solid silver. So now we've converted to moles of electrons, and we need Faraday's constant to go from moles of electrons to coulombs. Since we're going backwards, we're literally multiplying by Faraday's constant. And you can follow that with the dimensional analysis. Remember, you don't have to memorize Faraday's constant is this number of coulombs per mole of electrons that's given on the formula chart. Okay, now we're in coulombs, we're finally ready to use our current in amps to convert to the time. So 5 coulombs of charge are passing every 1 second. So now we just need to plug in our numbers, and we get to figure out how much time this took. Notice we're keeping 3 sig figs from actually both of our given numbers. Now they didn't specify a unit of time, so I just left it in seconds. But you can totally convert that into minutes if you want. You wouldn't be wrong, because they didn't specify. So now you've seen pretty much almost every kind of problem we could throw at you. Of course, there are many, many types, but there are 2 more problems for you to try. I know you're very excited. So you should go ahead, try part A, try part B. It'll be ever so much fun. And when you are ready to check your answer, unpause the video. All right, this first problem, they have given you the current and they've given you the time. So this is just the normal, are you safe? Calculation. So we convert minutes to seconds, multiply times the current, use Faraday's constant to convert to moles of electrons. Then we needed to convert from moles of electrons to moles of copper. Hopefully you were looking at the solution given, noticing that since copper is hooked up with 2 nitrates, this must be copper with a 2+ charge, which means it's gaining 2 electrons for every atom of copper that's being reduced. And then multiply by the molar mass for the win, and that's it. So in this circumstance, we would produce 11.9 grams of copper. Okay, there was one more practice problem, part B, and this one was a little weirder. It wanted to know how many moles of electrons must be transferred if we are producing 5.16 grams of copper metal. So we're starting with grams, we're starting backwards. But notice it's not the full calculation. We're only needed to calculate the number of moles of electrons. Well, before we can get moles of electrons, we have to get to moles of copper, right? So we divide by the molar mass, and then we can convert to moles of electrons. And since we're working with the same copper 2 nitrate solution, there's again 2 moles of electrons for every mole of copper. And then that's it. We wanted moles of electrons, that's where we're at. So 0.162 moles of electrons must have been transferred if we produced 5.16 grams of copper metals. And that's it. I hope you have enjoyed this rainbow-colored tour of dimensional analysis. And thank you for enjoying all of the glories of chemistry with me.